I'm at the University of Canada. Today I'm going to tell you a little bit about azulenes. My group is primarily a spectroscopy group where we look at energy transfer and interesting processes in molecules or how molecules interact. For instance, we look at eczema formation in some pyrenes and pyrene derivatives that have arms. We also have looked at using our photophysical knowledge to help in the design of pH probes. Specifically here we're looking at aminoquinolines in lysosomes. We also have delved into DNA origami, where you take scaffolds or long strands of single-stranded DNA along with short staple strands. You combine them together to make any structure you can imagine. Here I'm showing an atomic force microscopy image of our 2D triangles. But right now I'm going to tell you a little bit about our spectroscopy measurements on azulene. To motivate these studies, let's have a look at the solar spectrum. So here we have spectral intensity versus photon energy. This is our solar spectrum at ground level. And here is a typical silicon solar cell where you have your valence and conduction bands, and with a band gap of roughly 1.3. There are a few issues with this. You lose quite a lot of energy. Firstly, photons that do not have enough energy are not absorbed. So here all these photons with energies less than the band gap are completely lost. Even if you have photons that are above the band gap of your solar cell, you will lose some energy due to thermalization. And even if you have a perfect photon that has just the right energy to be absorbed by sort of the lower part of the conduction band, you still won't get all that energy out because of thermodynamic considerations with respect to your environment. So this leads to something called the Shockley-Kayser limit. You can see here we have efficiency versus band gap, and we have various sort of crystalline structures, monocrystalline or polycrystalline. So for a silicon solar cell, under one sum illumination with a single junction, the Shockley-Kayser limit is 33.7%. So here, this band gap is the band gap for silicon. So this is a bit of an issue, and we think we can enhance the efficiency of solar cells by using exotic energy transfer decay processes. In this case, something called singlet fission. So singlet fission is when you excite one of your chromophores in your solution, and that chromophore lives for a certain amount of time, and then you have a ground state chromophore that comes near to it, and this one singlet excitation can split into two triplet excitations. So you effectively absorb one photon and you can get two photons out eventually. So this enhances the efficiency of processes and devices like solar cells. There are a certain set of minimum requirements that are needed for singlet fission to occur. The first and most important is that your energy levels, in this case, are singlet first excited state. This energy level has to be twice whatever your triplet levels are, so that you can actually form two triplets from one singlet. It would help to have a certain long lifetime of your upper excited state, so that you have time to have another chromophore coming near to it. And then of course you need to have multiple chromophores present with the correct distance and orientation, so that from one singlet you can generate these two triplets. If you look in the literature, this is a paper from 2017, you can see that going from your singlet state to your triplet state, this is a combined state where your triplets still have spin 0. So that process, going from singlet to sort of this triplet state, can be very fast. It can occur from hundreds of femtoseconds to around a nanosecond, and then converting that into two triplets, that is the slow process. So for instance, this goes from around 10 nanoseconds up to 100 microseconds. And this is for a structure like TIPS pentacene here. So azulene can possibly undergo singlet fission from the point of view that it has really interesting energy levels, and it's very unusual for a conjugated molecule of this sort. So if you look at the energy levels that we have, so we have a ground state, our first excited state, and then our second excited singlet state, the gap between our S0 and our S1 is really small compared to most molecules that you'd see. For instance, naphthalene, it's completely different. This is due to the HOMO-LUMO-LUMO plus 1 molecular orbitals. So if you look at the electron density for your HOMO and your LUMO, the electron density is in completely different locations on your azulene ring, and that leads to low electron repulsion and therefore a very low S0, S1 gap. This actually has the great benefit that if we were to, say, excite into S2, and this is where we actually see the fluorescence from azulene from the S2 state, because as soon as we go to the S1 state, there's a conical intersection that tends to non-radiatively decay any energy that gets to that state. So our S2 state is reasonably long-lived, and also it's roughly twice the triplet energy level. The triplet energy level is very similar to your S1 state. So this looks like it's a good candidate for singlet fission. The problem is that the triplet state is so close to the singlet state that you get back inter-system crossing and you don't form that many triplets. So to help with that, if we put different constituents on the ring, we can actually change the energy levels of some of these S1 and S2 levels, and we can try to separate the triplet and singlet state a little bit and actually generate some singlet fission. So if you look at the spectrum of azulene, this is the absorption spectrum. There's a small amount of S1, but you can see S2 and then S3 in higher states. And this is azulene at 20 micromolar in solution. You can see the S1 state has a low, roughly 0.008 peak. So it has low intensity, but it's still there. So the first structure we looked at that was different from azulene was this calyx 4 azulene, or calyx as I call it. So here we had 4 azulene chromophores, and they are connected by bridges, and we wanted to see how that would change our singlet, first singlet and our second excited singlet states. In the case of the first excited singlet state, you can see there's a small redshift of about 1,000 per centimeter, but also this calyx here is 4 times less than the concentration of the azulene, but its intensity is roughly the same as your azulene. So that means that each of these chromophores are acting separately, and you're getting 4 times the amount of absorption from this structure. If we then look at our S2 state, and here I've just zoomed in, you can see that you have not just 4 times the amount of absorption, but you actually have 6 times the amount of absorption, plus the redshift is huge now, it's over 2600 per centimeter, and we have this extra sort of peak to the red side that would suggest that some kind of extra interaction. So in this case, for the S2 state, we think that these chromophores are kind of acting together and the excitation is delocalized across the whole structure. So that's it's pretty strange that we had for the singlet and the second excited singlet that we had completely different behavior. So if you look at the fluorescence of azulene, this is our fluorescence from S2, but then in the case of calyx, you see absolutely no fluorescence at all. So the spectral evidence that we used to try and guess at what the decay mechanism could be, we saw no S2 emission from the calyx at all, and from our collaborators who did some transient absorption measurements, we also saw no triplets visible either. We then had to try and eliminate all possible decay routes. We looked at things like the Forster energy transfer, but that wasn't going to be useful because the spectral overlap of your S2 and your S1 levels is very, very low. So then, looking at all these things, we decided that the only possible decay mechanism that could explain these results was via an S2 singlet excitonic fission process. So we have our S2 excited state. This goes to give us 2 excited singlet states, and that decays very quickly through a covalent intersection back to our ground state. So we do have kind of a fission process, but not the one we were expecting. Then we looked at the spectroscopy of benzazulene. So here we have our azulene and we've got a benzene connected to it. And here you can see that we have a lot of structure in our absorption and our fluorescence. Firstly, we wanted to check if SF is even possible in our benzazulene. From our absorption spectrum, we have our S2 level, and this is in methyl cyclohexane, of around 24,826 per centimeter, and we have our S1 level as well. For our triplet level, it's difficult to work out what this is because we can't see it. But if we assume that the singlet triplet gap is similar to what you have in azulene, then our triplet level is roughly 12,500 per centimeter, which means that when you take 2 times your triplet level, it is roughly equal to your S2. So this should show singlet fission. When you go from something like just our normal azulene to this benzazulene, you'll see there's a red shift. This is expected because you have a more extended conjugated molecule in the benzazulene case. Also, the structure is more rigid because you're now seeing these very large vibrational peaks. If you look at the distance between these vibrations, it's around 1450 per centimeter. This is due to skeletal vibrations in your ring. Then to measure the decays, what we use is something called our picosecond range fluorescence upconversion technique. This is where we have a short laser pulse, sort of tens to hundreds of femtoseconds, and we have our fluorescence from our sample, and these are interfered on a nonlinear crystal. If the phase matching angle is correct, then you will get this upconverted signal, and that's what we actually measure. So the reason why we can get a really fast time resolution is because the laser pulse is gating this process. So here we have our excitation laser pulse that's exciting our sample. We get this nice long fluorescence out of it, and then we send in this red laser pulse to assert that hits different levels of our fluorescence peak, and we get our some frequency pulse or our upconverted pulse, and we do that at various points across our fluorescence spectrum, and this gives us our picosecond resolution. This is just what it looks like in the lab. Here we have our nonlinear crystal. This is where the sample usually sits, and we have a magnetic stirrer because we're hitting it with quite a lot of laser light, so we want to make sure that we're not measuring something that's decayed already. This is what we look like. So here the excitation wavelength is right into our S2 region, and our detection wavelength is at the S2 fluorescence region as well. Here's the upconverted fluorescence versus time, and you can see these are tens of picoseconds. And we looked at our benzazulene for various solvents such as methanol, toluene, or methyl cyclohexane. So the S2 decay that we can measure using our quantum yields, and also looking at fitting our decays that we measured here, we can work out that our radiative decay is something like 10 to the 7 per second, so our rate constant. The rate constant for our non-radiative decay is roughly 10 to the 10, so it's larger. This kind of makes sense because we don't see a lot of or any emission from our S1. So there are many decay pathways that can happen in a non-radiative manner. You can correlate the sum of all these non-radiative rate constants from, in this case, our S2 region, with the energy gap between our S2 to S1 levels. This is called the energy gap law, and it implies that the S2 to S1 main decay mechanism occurs via intersystem internal conversion. Then for the S1 decay, it's very difficult to do this because we don't see any S1 emission, but we can kind of guess or calculate an upper bound on these. So our radiative decay rate constant is around 10 to the 6. Our quantum yield is roughly 10 to the minus 7. That gives us a non-radiative decay rate, which is really large. It's 10 to the 12. This is so large that it's actually faster than intermolecular vibrational relaxation rates in solution. So this implies that our S1 to S0 decay occurs via this conical intersection. So most of what we're seeing are non-radiative decay pathways. That was in solution, but then we just took some preliminary measurements on benzazulene in thin films, and we see a very different spectrum. So the blue is for our solution spectra or spectrum, and the pink is our thin film spectrum. So you can see the S1 region doesn't change much, but the S2 region is really different. You have a smearing out of all your vibrational structure. You also have a redshift. So we hope that we might see some more interesting dynamics there. Okay, with that, I'll finish. This is my group at the University of Saskatchewan. We have Darshi and Wenglong, who are doing a lot of this azulene work and pyrene work. Then Jaydeep and Ozra, they are really being pioneering with the DNA work. Also, most of our lasers are housed at the SSSC, so thanks to those folks. All our nice molecules, or azulene-based molecules, are made at the University of Saskatchewan in the group of Ken Gigino and Jonathan White. And our funding comes from NSERC, the Quanta Institute that's on campus, and also the university. So if you have any questions, you can email me at amy.stevens@usask.ca. But also I'd like to thank the organisers for inviting me to give this talk, and I look forward to listening to all the other talks from the conference. Thank you very much.